Can I give a little context setting? We've got a good cross mix here. Good morning, everybody. We'll get started because we've got a lot of folks in here. Some who traveled. So the purpose of today's meeting is for two groups to brief back to interested folks on some efforts that have gone on related to stormwater. And that's specifically mapping out where all of our infrastructure is, which is good and needed because we don't have it on a map, believe it or not. And then the second thing is a study, and that was done by the Eastern Carolina Council, the local council of governments. And then the second item for briefing is a study done by some folks from ECU, and I don't want to steal any thunder, so I won't go any further, on things to do with groundwater, okay? But this is really good. It's really good that I'm looking out here. I've got people specifically interested in flooding in their neighborhood. I've got people specifically interested on the strategic issue of just stormwater in town and water quality, and of course staff. So I want to set context for this because this issue is just bigger and wider than where all drain holes are. Not to belittle that. That's important. And what the groundwater is doing, because that's important. We have a flooding issue and a stormwater issue in this town, and it's mainly on the east side of town. And I love that the history committee put this photo up because this explains exactly why we have a stormwater issue in Pine Knoll Shores. A bunch of great people decided to put 5 streets and then a whole bunch of canals and houses and such. We put in a mobile home park and we built a golf course. And all that water that our creator wanted to go to this way to Hoop Hole Creek isn't happening anymore. I don't need to tell anyone on the east side of town what that does. Okay, that natural flow was stopped starting in the 50s. I hear a lot of folks say it's the golf course's fault, or it's Hampton Inn's fault, or it's the town's fault, or it's developers' fault. It's man's fault. Okay, we did all those things, and that water's not draining. In 2006, the town hired a hydrologist to do some studies to see if we could put some infiltration chambers right about here, right on Yolpon, the 4 undeveloped lots on Yolpon that flood first. And we were looking at that being a solution to some of the East End issues. What the hydrologist told us is what anyone on the East End already knows, and that is the flooding issue isn't necessarily just rainwater coming in across the surface, it's the water table of the town rising. Okay, the water table comes up, and then of course the rain, flooding waters have nowhere to go, and we have flooding issues. And essentially what he said was infiltration won't work. You can't put water in the ground if it's full of water. Hopefully ECU is going to tell us that here in a few minutes. So for 40 years, whenever we've had flooding, okay, we've pumped water to the ocean, to the sound, and to the canal. And the most recent time we did that was 2010, when we had the most severe flooding, according to the East Enders, in about 30 years. They said it was worse than Fran, Bertha, and such in 2010. So we started looking at it a little closer. There's four things going on in town, and I want all the disparate groups to kind of hear that. First, the town installed this system that we're all familiar with to try to drain water to the sound, and we pull that water from Myrtle Court, which is about here, And that's working to an extent, not to the extent that everyone would like to see, but in October this year, we kept pretty good records. We think we moved about 20 million gallons of water to the sound that otherwise would have stayed and recharged the water system. So we're doing that. We're monitoring the water table, okay, with monitoring wells that were put in by that hydrologist at Yaupon and in Hester Woods and at Myrtle Court. And Scott and Sonny are doing that. And they think they may have found the sweet spot, okay? That is the water table level at which, when we have a significant rainfall, okay, that's when we're going to see our most severe flooding issues. That's why a couple weeks ago, or a week ago, when we had that rainfall amount, we kind of knew we'd be okay, even though we were going to have 4 inches over 4 or 5 days, because the water table had settled just enough. It's really high right now. But that's what the town is doing. We've done this ECC stormwater work to identify where all of this infrastructure is. This is kind of a second item going on. And one interesting thing I think in town is that a lot of folks aren't aware of is that NCDOT came in the early 80s and widened 58. And when they did that, they put drainage along several spots along 58 with outfall into the canal. And that's largely non-functional right now. It has not been maintained by DOT, and we are going to ask DOT to come in and fix that and maintain it. And we think maybe that will help some of the stormwater issues, because all that water that doesn't drain into one of those 3 areas right there recharge our water table. The ECU study that we're going to hear about, the groundwater study, he's going to tell us about, I think, about groundwater. They didn't do the study just in town, they did it island-wide. He's going to tell us a little bit, I think, about where that water is moving. One thing that we want to do as a follow-on to his study, and that was, are any of the citizens who participated in the ECU study here? Good, great. He's going to tell us a little bit about that. Folks, we're thinking of coming back to you and asking you, would you like to continue working with the town to look at water quality, to use those same monitoring wells? And Scott's talking to UNC right now, across the way, UNC, to see if they could help us and use those same monitoring wells and see if our water quality is suffering because of this issue as well. So the ECC work, the ECU work, the monitoring that Scott's doing, working with Sonny, and then the improvements that we're looking to do on the east side of town to the existing stormwater study. There's 2 things that we believe, and I should have put this up on a slide and I didn't, but I want the academics to hear this too. This is one slide of the study done by that hydrologist in 2006. And Bob, this is what I'll be presenting to NC State. And the hydrologist came to the conclusion that the golf course pond network and reef-zone Bermuda greens, they act as huge wet detention basins, and they recharge the water table on the east end of town. And I've seen flooding now in 10, 14, and 15, and there's unquestionably a correlation between the pond level on the golf course, the pond level on Reefstone, which trips over to Mrs. Lee, and then how bad the flooding is on the east end of town. So we need to find some ways to address the Reefstone pond and improve improve getting water from the golf course pond network down to the sound. So I wanted everyone to have that as background, so you don't think just where all the stormwater infrastructure is, and and you don't hear just what ECU looked at with groundwater. Who wants to go first? Yours is up first. This is Lauren, and she's from our Council of Governments. She did the study here. You'll tell them about where the funding came from and all that business. So, thank you.
Okay. Good morning, everyone. I'm so glad you came out this morning to hear us speak. As Brian mentioned, my name is Lauren Tuttle, and I am a community planner with the Council of Governments. So back in the fall of 2014, the council applied for and received a grant. It was a Clean Water 205J grant, to be more specific, from the North Carolina Department of Environmental Quality, which you may previously known as DENR. I feel like we've all pretty much heard that term. And we received this grant to conduct a stormwater mapping project for the town. And in general, this grant project, this grant program is a federally funded program from the EPA, and it's administered by the state for various water quality management and planning projects throughout the state. So what I'm going to do today is I'm going to share with you kind of the results of that project and what we did. And then during the second half of my presentation, I'm going to go into some very easy things that you can do at home to help better manage stormwater runoff pollution. Oops. Does this work?
I'll hit that.
Oh, wait. Okay.
Try again.
Nope.
I'll do that.
Okay, great. So before I dive into our project, I kind of want to just go over what is stormwater runoff. You all may probably know what it is, but just in case. So stormwater runoff is produced when rainwater flows over the ground or hard impervious surfaces like parking lots, streets, driveways, rooftops. And it flows over these surfaces instead of soaking into the ground. And there's two reasons why the management of stormwater runoff is important. First of all, when stormwater moves over the ground or impervious surfaces, it can wash away and carry with it pollutants that may end up in our water bodies and may eventually affect water quality. The second reason why the management of stormwater runoff is important is because impervious surfaces prevent stormwater from soaking into the ground and therefore can cause flooding. So therefore, it's important that our stormwater infrastructure is maintained and it properly functions. Okay. So the biggest part of the grant project that we received from the state is we mapped out all of the town's stormwater infrastructure. And the pictures that you see on the screen, all of these pictures were taken in Pine Knoll Shores. So the stormwater infrastructure that we mapped included culverts, wet ponds, area drains, catch basins, outfalls, and then pipes that connected all these different pieces of the infrastructure. We conducted this mapping process over the summer and fall of last year. And how we did it is we used a handheld GPS unit, and we pretty much drove or walked every single street in the town to map out the location and the condition, whether it was what the shape of the piece of infrastructure was, or if it was clogged or that kind of thing. We worked really closely with Sunny with the town, and we also worked really closely with town staff to review our maps and make sure that we got all of the infrastructure mapped out. So once we were finished mapping all the infrastructure, we created two sets of maps for the town. One is this big poster you see over here, and if you didn't get a chance to look at it before our presentation, I encourage you to come and take a look at it afterwards. And the second type of map we produced is a portable map book. And what you see on the screen, and I know it's really hard to see, but pretty much that's one page from the map book. And so it just kind of gives you a more zoomed in view of what infrastructure is in each area. In total, we ended up mapping 54 area drains, 1 catch basin, 75 culverts, 26 outfalls, 1 wet pond, and then multiple pipes connecting all of this infrastructure. And as you can probably see on this map, we thought it was important to map out all stormwater infrastructure regardless of who owned it or who maintained it, whether that was the state, private it was owned privately or if it was owned by the town. And so we hope that these maps will be really useful to the town. So before I move forward, I just want to stop and see if there's any questions about the stormwater mapping part of the project. Yes, sir.
Thank you for this. Brian mentioned in his opening remarks these catch basins that were installed by the Department of Transportation along Highway 58 that drain into the canal that are not operative today or not maintained. I was just wondering, under today's rules, would it be legal to drain stormwater from Highway 58 into the canal?
That is a really good question, and to be honest with you, I do not know the answer.
Yeah, I think the answer is from a cold start, point source discharge isn't allowed. That I'm certain of. What they were permitted for in 1980, I'm not sure, John. That's what I want to. That's what I want to see. I mean, it's very possible that we're. I mean, I know that PKA fought DOT having those discharged for that very reason back in the 80s, but I want to see what they're permitted for. We're not even certain of that.
Or whether that permit would be grandfathered in. Yeah.
Don't know. You know, we obviously don't want to do something that we know is going to degrade water quality, but there's also, you know, the swales.
Right.
Part of their design is for treating water before it goes into the water, so into the canal.
Does anybody else have any questions about mapping? Yes, ma'am.
This was done only in Pine Hill Shores?
Yeah, so when we applied for the grant, and ECC has applied for this grant over the past, I don't know, I want to say 5 years or so, and every time we apply for the grant, we select a different municipality within our region to do it. So when we applied for it back in 2014, we applied for specifically doing it for Pine Hill Shores.
And I guess my second question is, you're talking a bit about water quality, and I see you have that concern up there. I thought our drinking water and all of that came from the Castle Hayne, way down deep. So we're not talking about the quality of drinking water?
No. And what I'm going to go into next, it's not specific to Pine Hill Shores. It's just kind of general things to make sure water quality. I'm not so much.
So we're talking about the quality of the sound.
Yeah,
okay,
exactly.
And that's important too.
Yeah,
okay. I just wanted to understand what we're talking about.
And I have to say, these tips I'm going to go into, I'm going to mention different potential sources of pollution, and these are just general tips. They're not specific to Pine Hill Shores. So I'm going to talk about fertilizers and pesticides, and I'm not trying to imply that fertilizers and pesticides are a problem at Pine Hill Shores. These are just general things that you can do at home. So, does anybody else have any questions before I move on? Okay. Okay. Yeah, that's okay. So moving forward, what I'm going to do is I'm going to discuss potential sources of pollution and why they're pollution and how they could harm water quality. And then I'm also going to talk about things that you can do at home. So starting with pesticides, fertilizers, and herbicides. So these items, they contain nutrients like phosphates and nitrates that when these nutrients get into the water, they can stimulate algae blooms and aquatic weed growth. And as these algae blooms and aquatic weeds die, bacteria uses oxygen to decompose these plants, which leaves limited dissolved oxygen in the water for fish, and fish need oxygen to survive. So one easy thing you can do at home is, don't apply these items before it rains because they might just get washed away. Use them sparingly, apply only what is needed, and also keep them off of hard surfaces. So with pet waste, also if you don't pick up your pet waste, it can also be washed into the waterways. And pet waste also contains nutrients, which I just talked about, their potential negative impacts on water quality. So therefore, it's really important to pick up, your pet waste and to dispose of it properly. And these are pictures of 2 signs that were actually taken in Pine Hill Shores. And as part of this project, I also kind of reviewed the town's code of ordinances, and picking up your pet waste is mandated by the town's code of ordinances. Litter, this is an easy one. So litter can clog storm drains, ditches, pipes, and when they clog these items, they can cause flooding. Litter also, if it gets into the waterways, it can entangle with wildlife or be mistaken by wildlife as food. And so, pick up your trash, reduce, reuse, recycle. And I just want to point out, this picture was not taken in Pine Hill Shores, so you don't have to worry about it. But I think it's a great example of what not to do. You can see a tire, a basketball, styrofoam trays, water bottles, and all of this is directly in front of a culvert. So.
Well, if you go down to the beach right now, you'll see some tires.
Isn't that what's washing up from the ocean though? Yeah, from that tire reef that was put in below those many years ago. Such a
So sediment or soil can come from construction sites, ditches, bare yards, and garden beds. And when there's excess sediment in the water, it can prevent light from reaching aquatic vegetation. It can also reduce plant growth and also decrease spawning habitat and cover for fish. And also, it can also clog up the stormwater infrastructure and prevent it from properly functioning. And the green grassy picture that you can see, I think that's a really good example of sediment that's kind of collected over time and clogged up a culvert. So what you can do is, reseed bare yard areas, mulch exposed areas, keep mulch in place, and don't pile dirt on hard surfaces because it may just end up washing away. Okay. Yard waste. So yard waste can be blown into or placed in the streets, and they can also clog up storm drains or ditches and can impede the water from flowing properly. So you can leave grass clippings on lawn, compost your leaves and grass clippings, or bag or containerize your yard waste. Household hazardous waste. Examples of this type of waste include any sort of paints, cleaners, or other sorts of household chemicals. These items can contain toxins, heavy metals, and nutrients. And when they get into the waterway, it can create an unsafe and unhealthy environment for aquatic wildlife and also for humans if they're in the water. And these substances could also bioaccumulate in fish and other organisms and potentially cause problems. So definitely don't pour any of these substances down the stormwater drains. Properly dispose of them, use them correctly, follow the instructions on the back. Auto fluids also contain a lot of the same toxins, heavy metals, and nutrients. Well, I guess not nutrients as the household hazardous waste. And again, they can create an unsafe and unhealthy environment for the aquatic wildlife. So, recycle your oil. I know the Carteret County Solid Waste and Recycling website, they have a list of all their sites that you can recycle oil at. Recycle batteries, antifreezes. If you have a vehicle leak, clean it up. I hear that kitty liddy works well. So I just wanted to throw it out to you guys. What are your stormwater or drainage concerns? I know Brian in the beginning mentioned a lot of the water concerns within the town. So if you have any stormwater or drainage concerns, I would be happy to hear them. I'm sure the town would be happy to hear them. Or if you just have any other general questions about my presentation.
I think the town is generally very observant of most of the things that you put up there.
Yeah.
The two things that I think affect the SA waters, and all of our concerns are about the SA waters, not drinking water. That's a great point. Are the roadways, the runoff, and as an aside to something that John just asked about, in the 80s when DOT did that widening and put in those drainage, as I mentioned, PKA folks at the time took issue with it and had some graduate students at Duke University do a study and they took water quality measurements before and after the project and believed that the DOT drainage degraded water quality in the canal and in Pine Hill Shores. So we've got to be very careful about what we ask to be done. tie this to our flooding / stormwater issues is the inundation of septic fields. I know, because I hear it from the folks on the east end, of septic issues when the fields are inundated for lengthy periods of time. So I don't have any data to back it up whether or not it's affecting the SA waters. I know they always close the SA waters for 2 weeks or 3 weeks after those rain events, so something's happening. I don't know if it's animal business or a septic field, but that's what I think our two largest issues here are in town. I don't think we have issues with a lot of those examples you gave, though it's good information to know.
Yes, sir.
Yeah, I just wanted to point out one thing too that's kind of a trade-off for us, and that is we're a tree city. You know, we like our vegetation, our big trees, but trees tend to shed leaves and pine needles, and they come down on the street and clog up our storm drains and things like that.
Could you go back a few slides?
And people who use those blowers, I mean, especially all the contractors in town who come and do your yard, they'll blow things into the street and figure it's out of sight, out of mind. You know, they don't actually pick it up.
Yeah, yeah. And these two pictures, they were not taken in Vinyl Shores, so I don't want you to think, you know, that the town's area drains are that badly clogged up. But I think with those drains, you know, the purpose of the grading is definitely to keep stuff out from flowing into the water. But if they're not cleaned up over time, you know, that's just a perfect example of what could happen. The picture on the top, it's just packed full of leaves within that drain.
So it's kind of like cleaning your gutters.
Yeah, pretty much.
Where in Vinyl Shores do we have these drains that I don't remember ever seeing them?
So if you look at this map, so the area drains are kind of like little rectangles on the map. They're pretty much everywhere. The bottom picture is what you call a catch basin, and I only found one of them in town, and it's actually over by the fire department over here. But the top picture, drains like that, and they're more, they have grates over them. They're all over town. So I think I forget how many maps, but I think it was something like 50 something of them.
Lauren, can I partially address that answer
Yes.
as well? Because I know a lot of folks out here are familiar with our flooding issues. Bill, in the 80s, the town installed kind of like what you see on the top picture on both sides of the road on 4 of the 5 tree streets, catch basins on both the east and west side of the road at about the 114, 115 address area. That Mr. Youngblood put them in, and they're of questionable use, I believe, because when the water table's up, there's standing water in them before the rain even starts. So that their point of failure when they stop absorbing water is long before any flooding issues. It was good effort. You know, I'm sure they were trying to do something at the time. But as we try to figure ways to improve moving waters to that vault at Myrtle, those things and those locations of those Sunny and Clark Edwards, as all of you know, is pretty involved in this. That system that they installed in the 80s is somehow going to tie in the solution to get to the water, to get the water.
Utilize those.
So we'll use them in some way, but that's where the cameras are. There's also ones on
Acorn.
Bob Curry Street, Live Oak, and there's some also Bill on these blue ones on the 3 ocean front streets. The old fronts.
Where do they drain into?
They're just drains.
Because they're the roads that flood all.
They're infiltration. They don't drain to a body of water. They're just kind of big. The big French drains.
Yeah.
They go straight down, and then there's a pipe 15 or 20 feet in each direction that's perforated. It's supposed to be a big French drain. Water goes into the ground. Problem is, if the groundwater is
Yeah,
up,
what's above that?
then so.
On the far east end, are those two of those?
These are, actually, can I invite people to come up to look at this so we can talk about that? I mean,
Sure.
don't want to come up and get a better look at this, so. Yeah, can't read.
Am I the only one?
I mean, so these triangles, they are culverts.
Oh, okay.
And to go back to your question about the drains and where do they drain to, pretty much.
These are the condos?
Yes.
Yeah, okay.
Yeah, so on this map, we have put pipes in there. So for a lot of these drains, you'll see like two little lines coming out of the drain, but they're not leading to an outfall or anything like that. And I think that's what Brian was talking about, that these drains don't drain anywhere. So you can definitely see that on the map where everything drains to.
They're meant to be all of them, with the exception of the DOT ones on 58 and the system we put in. All of them are infiltration. And as I said in the beginning, infiltration doesn't work if you're infiltrating into a water.
How do you clean the silt out of them?
So, good question. Last year, for the first time probably in many, many years, Sonny brought in essentially a roto-rooter followed by a
big
jet vac
Big jetter.
guy. And he's got some great pictures of the gunk that they pulled out of it.
12-foot roots.
When I say roto-roots, so, you know, our study begs the question, what are we going to do with all this? Well, one, we're going to ask DOT to fix theirs, and two, we're going to start maintaining ours. We're also going to press private homeowners where appropriate to fix theirs too. So roto-root followed by jet vac, and we did that in most of the ones on the east side last year.
And at first, y'all, they wouldn't even work. And it was after they dreaded it out, they started working. That's true.
Yeah, and then, you know, they reached point of failure when we had 8 inches of rain in 6 hours on 19 November. And we're never going to solve the problem to fix, or divide the problem to fix that. But
Is that the day the highway flooded?
yes,
Well, we know why.
right.
The water table was down.
Yeah, what Sonny's referring to, the day the highway flooded, one of those DOT drains is right in the right-of-way on 58 in front of Pine Knoll Towns. And the outfall for that is at the canal off of Arborvitae somewhere. And the outfall at the canal is blocked. It's closed.
Completely blocked off.
And I don't want to mess with it until I get the DOT folks out here to explain what's going on with it. So.
All right, well, thank you, everybody.
Thank you.
Several years ago, we were out in Emerald Isle doing a water study, and what we were trying to do there was sort of what we've been trying to do across the entire island. And so we wrote an article, if you go to the next slide please, about how marine inundation and groundwater inundation, again these are just technical terms, I'll explain them in a second, could impact barrier islands with respect to certain sea level rise scenarios. So from our perspective, we're scientists, we like to think, and so we're sort of doing these projections. However, this study then precipitated some questions, and those questions were, well, we're just looking at Emerald Isle. What is the extent of the level of the water table across the entire island? And from a scientific perspective, a research perspective, we said, well, if we're to do the same study across the entire island, what would be that? What would be that result? And so that got us to thinking. However, the same ideas that we had could apply right now with respect to what is currently going on at the island. In order for us to make these projections, we need to figure out what's going on right now with respect to the water table. Where is the water table? How deep is it? Where's the groundwater flowing? And so on and so forth across the entire island. One of the questions that I was asked by Frank Rush when I did the study in Emerald Isle, he said, well, where's the groundwater coming from? In which direction is it flowing? Well, we only looked at Emerald Isle, and so we couldn't definitively answer that question because our focus was just on Emerald Isle. To answer that question, we need to look at the entire island. And so we have some insights and perspectives as to what that might happen. Next slide, please. And so to move forward, we came up with a research question, since we're scientists, and that is, what is the impact of groundwater or stormwater flooding on boat banks? And so what we hypothesized was that, as has been explained previously, the water table at some points might be really close to the land surface. And at some points, it is possible that the water table might be above the land surface. So if the water is really close to the land surface, let's say it's below the land surface, but just slightly below, that means you don't need a lot of water in order to saturate the soil. And so when it rains, that water doesn't go into the soil, it then floods your streets. In some cases, the water table actually gets to be above the land surface. And so again, there's a no-brainer. Then you're going to have exacerbated stormwater flooding issues. But then the question is, how deep is it typically, to the water table? And so if you can get a handle on how deep the water table is, perhaps you can come up with mechanisms or processes in order to address that situation. And so we need some baseline data. And so the interesting thing about groundwater data is that if you just have a single point in space, if you just have one well on that map, that one well is not sufficient for you to create a surface, because the water table, by definition, is a table, is a surface. So you can't get a surface from a point. You cannot get a surface from 2 points. The best you can do is get a line, right? And so what we want is a surface. So in order to get a surface, we need to put multiple points across our area of interest and then come up with a surface that joins all those points together. So that's what we need to do. However, we need to get the water level data from all those points at an instant in time, at the same time. So if you had data from 10 years ago and data today and data 2 months ago, you cannot create a surface from those points, because the water table does this over time. So who's to say that 10 years ago data and 2 months ago data is at the same instance in time? You'll be mixing apples and oranges. So in order to get a surface, you have to collect data at one instance in time. So the goal is to put in these measurement points across the entire island. So we have to drill wells, because those are our windows into the subsurface to figure out what the water table is doing. And so to measure the water table, we can do it in 2 ways. The first is we can install water level loggers, which are just automated devices that just dig down a well and then it records the amount of water above the logger. Then we do some math in the background and figure out the elevation of the water table with respect to The other way you can do it is you can have people go out and measure the water level. And then in this case, they're measuring the depth to the water level. And then again, go in the background, do some math, and then convert that to an elevation. And so if we have those water level loggers, it costs a lot of money. It's $500 a pop for each of those water level loggers. And so if we have 30 wells, we currently have 29 or so. If we have 30 wells, that's $15,000 in order to just buy the devices, not including the cost for installing the wells. However, if you involve people, and if people have free time on their hands, they could perhaps help us, so you can get a much more broader distribution at lower cost, and then you also involve the people into the project, which means, I was just reading the mission statement for Pino Shores. It says, encourage the participation of residents in service to the town and community. And so again, that facilitates the mission of the society. And so when we're developing this project, we said, what could be those mutual beneficial aspects where, as a scientist, I'm just looking at the groundwater data and projecting, thinking in the future, but then can we involve the stakeholders as well, the towns and municipalities and the residents, so that they could also benefit from this project. And so that was our thrust into this study. Next slide, please. And so both on Emerald Isle, what's interesting is that, which is very evident, since we did this study there in the first place, is that you've got these dunes and swells. So I don't have to preach to you, since you're the choir. But what's interesting with how this intersects with groundwater is that if you're in a dune, you're really high, and the water table at that location is very deep. If you go to a swell, right, then you'll be closer to the water table. And so the regions where you'd expect to have these flooding events when it comes to groundwater going above the land surface will most likely be where you're possibly in a swell because you're closer to the groundwater at that location. And so the topography plays a role with respect to where the water table is. And so with respect to mapping of this water table, that's why it's important to create the surface rather than just having a point measurement. Because if you have a point measurement, who knows, you could be on a dune, and you could be the water table could be deep by definition. And in some cases, who knows, you might be in a swell, and then the water table might be very close. And so you might get biased estimates if you're just looking at that one point. And that's why we need to have multiple points and ultimately create these surfaces representing the water table. Again, this goes without saying, the motivation of the study is stormwater flooding. And so from your perspective, how can water table ideas and knowledge of the water table influence how we address the situation? And so not only does Pioneer Shores have this problem, but Emerald Isle and other municipalities have this problem, and so it's a concern on people's minds. So, in terms of these broad perspectives, what were our goals? There were 3 goals that we're trying to achieve. The first was, could we involve citizen scientists in a research project? Citizen scientists were just participants. One of the questions I get asked is, who or what is a citizen scientist? How is that different from just a participant? Well, with citizen scientists, the idea is that we involve you in the process. And so in some cases, you might have thought I was putting the burden on you as a citizen scientist, right? But well, that's why you're a citizen scientist. You are involved in the discussion. So we talk about, the issues, and then we talk about, how we process the data, and then we try and understand the system together rather than me just saying, go and collect data over there, right? If you just go and collect data, you're a participant or volunteer. If you're involved in the discussion, which is what we try to do with this project, then you're involved in the thinking and the science behind why we're even doing this in the first place. Okay? And so the next goal was to assess the effectiveness of water level measurements from citizen scientists. So, okay, yes, you can collect the data, but are those data robust? Do we have confidence that you're actually collecting reliable data that we can then use later on and say, well, based on this data, we can make these alterations and modifications. So we need to have confidence in your data. And so one of the things that we tried to do was to assess whether those data measurements were robust compared to the loggers that we buy but are more expensive. And so I'll show some results about the robustness of the data from this project. Ultimately, we also wanted to assess the perceptions of the citizen scientists. So if you do participate in this study, do you come in and leave with the same knowledge? Do you benefit in any way? And so we try to include some mechanisms to assess how the interactions perhaps had changed what you think about the system with respect to groundwater systems. So, what is citizen science? A lot of people have come up with multiple definitions. I like this definition because it connects collecting the data with the process of learning. And so you are expanding scientific knowledge and literacy, but then you're doing something. So again, it's not just volunteerism, but then in that process, you're also trying to learn about the system. And so some people say groundwater flooding, some people say groundwater inundation. So what is groundwater flooding and what is groundwater inundation? From our perspective, what we're trying to do is, as scientists, create a baseline and then project in the future and say, if indeed sea level rise is going to occur, what would be the ramifications of sea level rise on the groundwater system? And so the current situation, consider the blue lines. So I'm going to move over here for a second. So the blue lines represent the current situation. So here's the water table, and then this is the sea. And so the water table is controlled by the sea. If the water table moves, if the sea moves up, then the water table moves up. If sea level moves down, then the water table moves down as well. These other blue line down here represent the interface between salt water and fresh water. So again, there's salt water coming in from the sea, but then there's this wedge that goes all the way inside, and everything in here is fresh water.
Dr. Mandan,
Yes.
you just answered a question that I've asked a lot of folks. So are you saying the tide,
As you know.
the sea level, the tide is affecting the groundwater level. Right now the groundwater level is X, and it'll, when the tide is lower, the groundwater, the freshwater groundwater will go down.
Yes. So technically, yes, but then I'll make the distinctions. And so we'll actually see the results in the plots that I'll show you. So sea level, give me a second, I'm coming to you. So sea level is sort of defined within a certain bounds. So sea level will be at a certain location, so that is sea level. And then the tide is doing, so here's sea level, then the tide is doing this, above sea level.
Right.
All right, so daily, it goes up, it comes down, and so on and so forth, but then this is sea level. So we could have sea level doing that, and then the tide will be doing this above sea
That
level.
was kind of my question. Are we talking big picture sea level, or you're saying that the water level, the tide level is affecting daily our groundwater level?
Both. So we're talking about big picture sea level, which is what I'm talking about, but even with the tides doing this, and I'll show you the data, it's very interesting, you can see an impact. So when the tide goes up, the water level goes up. When the tide goes down, the water level goes down. So there's that combination.
Naive questions. It seems like what we're concerned with here is called water table, not groundwater, water table. Reference to the center of the earth, if you took both banks, would the water table be the same distance from the center of the earth across all both banks?
No. And so
why?
Let me clarify that. A good question. All right. So first of all, groundwater is the water that's in the subsurface. The top of that groundwater is the water table. So this is in terms of technical terms, when I talk about the water table, it is groundwater by definition. But then the water
It's
table.
not in your picture though.
Well, so here's the water table.
Yes.
That's the top of groundwater. So everything here is saturated. So this is groundwater.
Okay. If I was to look at the water table, what
Which is
would
just
I
the top
see?
surface, right?
What would I see?
And
So it's like wet sand?
if you and this is where we have the groundwater wells. So in order to see the water table, we need to have a well. And I'll show you how we install the wells and how we record water levels in the subsurface. And so here's a good description. If you go out to the beach and then you dive into the sand, at some point you're going to encounter water. There's the water table.
Okay.
All right.
Last question. If you had a lake, would the surface of the lake be the same distance from the center of the earth as the water table?
No. No, because it depends on the topography. And so I think that's one of the other questions. So the water table will have a different profile depending on certain conditions. So it's not going to be flat, which was your question, right? So the water table is not going to be flat. It will have, most likely have some curvature to it. And depending on recharge zones and discharge zones, basically, where's the water going into the water table? So if the water is going into the water table, it's going to be mound-like. It's going to be like a mound. And then if it's discharging, it's going to level off. So here we go. The assumption here is this is higher than here, and there's a slight profile. There's a curvature to this line. And so water is coming in here, and then it's discharging there. So think of it like a slide. So if you're sliding down, why do you go up, down, rather than down, up? You are in a gravitational potential field. Similarly, here you are sort of in a potential field. This is high potential, this is low potential, so water is going to flow from high to low. And that's how we know the direction of groundwater flow. Ultimately, when it comes to that question, we're going to say, where is the highest potential? Over here. Where's the lowest potential? So over there. Therefore, groundwater flows from high to low potential. But then that line that defines the top of the groundwater is not going to be, it could be flat, it could be at an angle or at a different angle, and so it's not uniform with respect to the center of the earth. In addition to that, going back to Robin's question, we get the water from the Castle Hen aquifer. So the Castle Hen aquifer is a deep confined aquifer. It too has its own potential field, which is different from the potential field for the superficial aquifer. So currently we're in the first package of sand that is on the earth. And then there's another layer below that, which is a confining layer. And you have another aquifer, then you have another aquifer, then you get to the Castle Hen aquifer. And all those aquifers are separated by these confining units, so they are distinct. And so the Castle Hen has its own potential surface. The surface has got its own potential surface. So with respect to the center of the Earth, different aquifers will have different elevations in terms of the water table. Okay. So what's the main point of this slide? If you have sea level rising, you move from this blue line to the red line, and then so this red line presents conditions where the water table moves up. But then notice what happens to these zones, for instance in here in these wells, where previously they were dry because the water table was below the land surface. But then when sea level moves up, that blue line goes to the red line, and now the red line is above the land surface. And so everything below the red line is saturated. But then since here you're not really in this is the subsurface, it's going to be wet. This will be ultimately wet. This will be always wet because of the water table. And so that's future climate change. However, that scenario happens when there's precipitation. And we'll show you some data when we do get a lot of precipitation, the water table rises above the land surface, and so it's wet because it's the water table that's rising, not necessarily that there's stormwater runoff coming into that zone. Obviously, it's going to be a double whammy, right? Because it goes without saying that stormwater will run into those zones, but the water table is doing this, and then stormwater rising. So if you're coming up with a plan to fix that, you also have to keep in mind that the water table is influencing that situation. You might solve the stormwater runoff, but if this is still occurring, how are you going to get rid of this water?
I'm not talking about big picture sea level. I'm talking about tidal influences.
Right.
When we're looking at real-time flooding issues, we're thinking about what the water table is at. We're thinking about predicted amount of rainfall.
Right.
Should we also be thinking about the tides? Or is that so insignificant?
So our data suggests that it's insignificant. So we have the tidal range. If the tidal range is perhaps in the order of half a meter, 3 feet, yeah, let's say 3 feet, or 3 feet to 1 meter, 1.5 feet. Tidal range is 1.5 feet. When we look at the water table, it's probably in the order of inches in terms of how much it's moving up and down.
Inches?
Inches. Right.
Well, it takes time for the tide to get to the sound to rise as it rises in the ocean. It's not at the same time. So there's a time lapse between the rise of the tide at the ocean and the inundation in the land, is there not?
With respect to tidal?
With respect to tidal.
Right. So, well,
And it would be different between the sound and the ocean.
okay, let's go to the next slide. Let's see if that's the next slide. So keep on going. Yeah, I'm going to the data now. Keep on going until you see a plot. Keep on going. Some pretty pictures. Keep on going.
Come back to these though, because I want to see what you
Okay. Keep on going. Keep on until you see a plot.
Good.
Keep on going. One more. No, keep on going. Again. Again. Keep on. There we go. Alright. So you see those little ups and downs when we have when we're done, you can come and actually look at the map. They're really evident. And so I had my graduate student looking at this and trying to figure out what was that influence that you're talking about. So indeed there will be a lag. And so the closer you are, the less the lag, but then the further away, the greater the lag. But you do have these semi-diurnal, if not diurnal tides. So when you see them going up and down in a day, you also see the same signal occurring here. But then if I was to zoom in this location right here, I would see it kind of going up and down, but that would be in the order of, since this is inches, right? It's in the order of inches. So it's maybe this peak, right? So all of these little peaks, it should be smooth, smooth curve. So it goes up, then smooth, goes up, then smooth, and so on. But then it's going like this. It's going up, but it's doing this. So all that is tidal signal. So the magnitude of those high amplitude peaks is in the order of inches.
On groundwater.
From the,
On
yes,
the water table level.
on the water table, right? So this is water table data.
I understand what you're asking, Bill. I mean, I live on the White Oak and I'm 3 hours behind high tide, listed high tide. So you're saying the sound high tide is different than the
Well,
ocean.
there has to be
Yeah,
a
of course.
time differential.
Right, there's a lag. But then you can see that signal propagating inland.
Brian, just to, on one point, like in Atlantic Beach, you know, the intersection of the Causeway and Highway 58, when we have a big rainstorm there and that intersection floods, it's usually at high tide, And that's because the high tide affects the outfall. They actually have pipes running from the street to the sound or to, you know, and when you have a high tide coinciding with a storm, the water backs up in those pipes and it doesn't drain. So that's separate from the water table.
Right.
Yeah, I mean, you do get a more flooding.
I ask those questions because we're trying to figure out all the variables
Right.
we should be tracking when we're trying to predict, do we pump, do we this, do we that? Now I was wondering, oh geez, do I need to look at the tides too?
And so I think that's a good point that you bring up, because one thing I didn't address here is this marine inundation. So the marine inundation is basically the water in the ocean taking over dry land. So there's that aspect. But then, so that's just one aspect. That aspect is, what about the groundwater? So as Brian is suggesting, there are those two components that you have to keep in the back of your mind. But we can have that discussion when we look at the maps later on. It's very interesting. Next slide. And so, to answer some of our questions, how do we involve citizens, how do we collect data, how do we assess the robustness of the data? First of all, we have to install groundwater wells. And secondly, we have to engage people that are concerned, right? So different stakeholders. We talked to the North Carolina Coastal Federation, we talked to municipalities, Emerald Isle, Pino Shores, Atlantic Beach, homeowners as well. And so we had to involve all these people in a discussion that could facilitate us putting wells in certain locations. And so, where are we going to put the wells? Who's going to own the wells? And so, as the town, you own some wells, okay? And so you can have them as long as you want them. If you want me to remove them, I'll go ahead and remove them. But they are your wells. If you want to keep on using them, and we'll have this discussion later on with Sarah about continuing this study, because we only have a window of, let's say, a year. That's not sufficient for you to have a baseline, because perhaps this year is an unusual year, right? So we need to have a much longer time period in order for us to get a really good baseline. So if we have these wells running and people collecting data, then we'll have a much more robust data set to work with. And then we have, once the wells are in, we have people to record the data. Well, they have to go out and record the data. And then ultimately, once you do record the data, well, what does it mean? Because the number that you derive from the well measurement doesn't really tell you anything. You have to process it, and then you have to come back to the table and say, this is what it means. And this is part of that discussion with respect to what do the data mean once we do the water collection. So we currently have 29 wells across the island. Several wells in Emerald Isle, Pino Shores, Atlantic Beach. And so this involved doing some reconnaissance. So where can we put the wells? Who can give us access? And so once we do find out, once we do get permission, we're using a device, a machine called a geoprobe. And so ultimately, a well is just a pipe in the ground. So that's what that is. It's a pipe that's perforated. Okay, so it's got slots. So here's the pipe, very thin pipe. And then at this point, it's a solid pipe, but under the ground, it's got slots in it so that the water can move into the pipe. And so what we do is we go and say, well, where is that level of the water in that pipe? And so we use certain devices to measure that. And so that's what is the useful information. And that's why these wells, I call them windows into the subsurface, because they allow us to see and determine where that water level is, so we can then create the water table surface that we want. And so I have a graduate student, James Owers, who was helping with this, and another student who is now taking a measurement to figure out how deep that well is. And when we're done, you might have seen this, there will be, we have to protect the wells, so we have a casing and a lock, so that nobody can go and tamper with these pipes. They're just PVC pipes, and perhaps somebody might even put contaminants in them, so they have to be protected. And so this is what we do. We come to a site with a geoprobe. So just give me 5 seconds for each slide. And then sometimes we have to fit them in really tight spots. And then here we are then using the geoprobe to drill the well and collect data. We're also interested in the sediment itself. And so in this barrel, we actually have the sediment that we extracted from that location. We go back to the lab and then we analyze the sediment. And so it's not just sand, right? you've got different types of sand, it's got different components, and so we want to figure out well, what's in the sand.
Find any oil down
The wrong place for one. So here we go, then sticking in the pipe in the ground. So ultimately, that's the well, just that pipe. Next slide. We can just skip this. Students were having fun. So here we are with the well, taking a measurement. And there's James, and then here's this water level logger device. All right, that's the one that costs $500, but it measures the height above the water. Yes.
Wouldn't your groundwater level be different because of the lay of the land? So how do you know if I put a pipe or a monitoring well on a 50-foot hill versus one on a 10-foot level?
Yes. And so, recall I said we have to do some processing in the background. So when you do measure the depth too, depending on where you are, yes, you might have a different depth here and a different depth there. So what we need to do is we need to convert those to elevations from sea level. And so then we go and do some math and then get heights. And so this level will be here and that level will be there, which is fine. So in this case, it's apples and apples, rather than doing a depth too. And I'll talk about that a little later on.
Just to follow up to the other one before, if all your measurements are relative to the surface, how do you know that the water table is curved relative to the center of the earth?
Well, again, it's not relative to the center of the earth. So, and in any case, what's important is the relative differences between those two locations and not necessarily to the center of the earth. And so that's I'm essentially getting a gradient, like a slope in mathematics. So with the slope in mathematics, it doesn't matter how high these 2 points are. So from the floor, here are the 2 points. It's the same slope. Can I have a ruler? Or here we go.
It's okay. I was just trying to use the water table as a reference.
All right, use the table as a reference. So here's the slope. So we can measure from here to here, here to there. Here's the slope. I can bring this down here and measure from here to here and here. The slope will not change. What's important is the slope, not necessarily the heights. Because that's what drives groundwater flow, the slope.
Does high and low tide have any effect on that measurement?
In general, yes. But then what typically happens is that, depending on where you are, if the lag time is minimal, it's not going to have much of an effect. So as we were talking about previously, where the water levels will go up and down with respect to the tide. So if you're far away, the signal will take a long time to get there. But if it's negligible, it's not a big deal. And the other thing is that range in the high frequency variations with respect to tide is very small. And so in the big picture of things, those little squiggles don't amount to much with respect to the slope. And we can discuss that when I show you that later on.
I understand why you made the conversion to sea level for your island-wide study.
Right.
What I think we want to do, and I'll say to your grad student and Scott, and I think this ties to what Paul was asking, what I think we want to do is convert all these readings against ground elevation at spots in town. Do you understand what I'm saying? That's what's important to us, not sea level. What I want to know is how is the water table moving with a certain amount of rainfall and affecting Loblolly Road at elevation +6, I'm making up a number, as opposed to Juniper Road at elevation +3. So if all of your calculations are at sea level, that's great, and I understand why you're doing that. But our particular interest is where those water tables are level relative to real elevation at spots in town. So just mention that.
But certainly he's got these points that he's measuring by GPS, so you know precisely where they are.
Yes.
And therefore your elevation can be just translated against
Yeah,
whatever
oh yeah,
elevation
yeah.
you want
I
to
mean,
use.
I assume you have XYZ data on all of those locations, all three.
I mean, it's easily transferable.
Right. But so to that point, we will address that, and I'll show you the graphs in a second. And so it also helps with the thinking, because it's easier to think about having some data. So this is just zero moving up rather than going down with the depth. Yeah. And so again, that was a challenge. I'll quote the perceptions of the participants. One of the challenges that the participants went to encountered was that I took it for granted. I said, oh, you go and measure the depth to the water level. And so they measured the depth to the water level. And then I come back with my maps, and then my map's saying elevation. And so they're like, whoa, you know, we were measuring depth, and yet you're showing us elevation. And so it's easier to think in terms of base elevation moving up rather than going down, because who knows how high, if you're on a dune, you have a different depth. If you're on a swell, it's a different depth, so it's harder to conceptualize that way. But I'll address your concern.
Yeah, I mean, I agree. It's very easily done. I just want to mention for your grad student graduates and runs off that's the data I think that would be important to us, how those water tables are relative to real. Well, maybe you did it already.
Well, we did it with elevation, so
Okay,
we'll
good.
we'll address it.
Sorry. Stop.
So here we are, just so we have the site. We have lots of people working on putting the wells in. Next slide. And then we try, and some people had been working, others are working hard, and we try and then clean up the site. So when we leave, you know, it's as if I've never been there. So again, we're respectful, we're appreciative of the opportunity to work, because again, we're doing some science. But then again, we want to keep these places looking as nice as they were. One component that is sort of big in this is the engagement. And so the idea here is that, again, you're not just volunteers, but we're engaging not only with the community, but with the actual people that are collecting the data. And so it's sort of a back and forth. We're not driving this bus, you know, we're all in it together on trying to figure out how can we learn and how can we improve on our environment. And so ECU is big on engagement. So how do we get participants? So we had our primary partners and secondary partners, and then also engaged stakeholders. And so initially, my initial point of contact was the North Carolina Coastal Federation. And then from there, they said, well, why did you talk to Sarah? Why did you talk to this person? And so then we had these other people that came into the picture. And so for the study, with respect to citizen scientists, we wanted to get 10 volunteers. And at the time, we had 20 wells. And so the goal was to have at least 2 wells per volunteer. We ended up with 8 volunteers signing up for 15 wells, and so we thought that was going to be good enough. And then when everything was said and done, we had 7 volunteers follow through for a total of 12 wells. And so some of the results that I'm going to tell you with respect to how robust was this data from the 7 volunteers who had recorded water level data from the 12 wells.
Can I ask a question before you leave?
Sure.
I see Pine Mill Shores, Emerald Isle, and Atlantic Beach. Indian Beach isn't am I the only well in Indian Beach?
Yes, you are. And then so you're really close. And so the
yeah, I'm really close to, actually
right.
My backyard is in Pine Mill Shores.
Right,
I'm right on the border there by the condos.
Yeah, so you're the only person there. And so I do acknowledge the homeowners. I didn't acknowledge you here per se as a homeowner. I acknowledge you there. And so the reason why these are sort of bunched in this manner is because they are the owners of the wells.
Right.
And then so the town has 12 wells, town of Pine Shores has 12 wells, and town of Emerald Isle and so on. So all of these are well owners. And then with citizens like yourself, I acknowledge you at the end of my talk.
No,
So
that's
you're
fine.
both.
I wasn't looking to be acknowledged. I was just trying to find out. I think my overall question is Indian Beach doing anything about this? It feels like not.
The other challenge was trying to find the right locations for the well. So I had to get good special distribution and so there were some places where it was really hard if nobody volunteered their property to get a well. And so what we tried to do was to go to the towns and say, then the town would say, go to the park. And so we can bring the truck in the park, you know, we've got so much space, and we know that, you know, we will be guaranteed that, you know, he's going to sign off the documents and yes, I'm the well owner. And so that's a lower barrier than going to individual homeowners. Some of them didn't want to sell their property. Next slide. And so part of the overarching goal here is to engage citizens. And so we said, well, have an understanding of how groundwater moves. So perhaps I should have brought my models again. Then they could have addressed some of the questions that people have. And so I have these groundwater models, and then they show or where the water level is in the subsurface. And so I put water in this model through this bottle, and then the water flows into the model and flows out. And so these pipes, which act as wells, and you can actually see the water level, and then that represents the situation that we have on bog banks. And so there was this educational component to try and educate the people participating, so that when they're collecting data, they sort of have an idea of what's going on in the subsurface.
You might have said this, but depth of these wells?
The depths of the wells, can you remind me, James? What's the minimum, maximum depth?
Minimum was 7 feet, the maximum was 27.
7 feet minimum, 27 maximum. And then obviously the 27 goes without saying was on top of a dune. Next slide. So how do people collect data? They use a water level meter. So you get a depth to the water level. I'll explain how we convert that to an elevation. And then we said that everybody should collect data once a week on Friday at 10 a.m. Again, you need a time slice, and so everybody has to be committed to collecting data at that time, or close to. So if you're off by a few minutes, a few hours, it's not a big deal. If you come the next day, then the data get really tenuous because, as I'll show you in the curves, water levels might go up really quickly and then they go down really quickly again. And so we need to be exactly on point with all those measurements to create the surface. It was over a 10-week period, and then the data were recorded on a piece of paper. And then for some wells, we also had those loggers to then compare manual versus automated and see how robust the data were.
Were your automated loggers, did you have to go to the site to read the automated loggers, or could you get them offline?
We had to go to the site to collect the data from the loggers.
So here's an example of the data sheet where you have to collect the data. You have to state the date, the time, and then there's some other columns, and I'll come back to this later on with respect to collecting water level data. Next slide. And so when you have precipitation is the major driver of the elevation of the water table. And so we should expect that when you have these really high precipitation events, the water table will also go up. And so that's why I said we needed to convert the depth to an elevation, because again, in your mind, lots of precipitation, water table should go up. If you're doing a depth 2, it's going to do the opposite. And so you sort of get lost, right? And so to make it consistent, we had to convert all those to an elevation. Next slide. And so we said, well, let's compare citizen scientists to water level loggers. And so the black dots represent the automated logger, and then the white dots represent the citizen scientists. And so what we're hoping for is that those two dots would overlap, and looking at the data, it seemed like they were really good data. They were mostly matching. So the logger gave us a value, and then the citizens were within a certain elevation that we thought it was within good error. And so we said, they're doing a good job. Okay. Next slide. There were other instances where I said, well, we don't have loggers in all the wells to make these comparisons, but could you compare citizen versus citizen and see whether one citizen is going to do better than the other citizen? And so for the most part, the answer was yes. The only challenge is, which is going to be part of in terms of the discussion, there isn't the same level of consistency. All right, so some people, it was voluntary at the end of the day. We're not forcing you. If you want to give up and do something else, that's fine. But then we just lose out as a scientist, because if we had a logger there, the logger would give us the data. But if somebody volunteers and then they don't collect the data, then it's a data gap, right? And then we won't have data for this black and red line. There'll be nothing in here, and so it's a loss for us. Next slide. So these are the data that ultimately, when they're processed, this is what you see. Okay, and so we have elevation. I've converted this with the maps on the table to inches. When we're doing such work in science, we have to convert everything to meters. And so there's meters here, but for the maps on the table and the graphs on the table, they're with respect to inches. So it's elevation, so it's with respect to sea level. So sea level is our 0. And so we have plotted the blue line with the black dots. This is the groundwater level, whereas this red and white line is the ground surface. And so this sort of addresses what you're talking about. So how far down is the water level from the ground surface? And so here it's really deep, and then you get a precipitation event, it goes up, and then it's really close to the surface. And then the same with that one. And so we have all those time series put on the table, so we can then see those relationships between the groundwater and the surface.
And those are specific wells?
And those are specific wells, yes. So each plot represents a specific well. So that's the well number, different well number. So I'm just giving you a couple examples here, but the rest of the data and the plots are on the table, on the maps. So this one is more interesting because, again, so you see what's happening here. It's a different location, and so you're closer to the ground surface there, and you're also closer to the ground surface there compared to the previous ones. And so what's very interesting is that it turns out, in this particular case, that the sampling frequency, the number of times, the length of time in between measurements impacts the result. Next slide, please. So when I did the comparison, I said, well, okay, so here's what the citizens did. That's the first graph. And then the second graph is where I had the logger. But because we said just sample the well once a week, whereas the logger is recording every 10 minutes. Okay, so this is every 10-minute data, and this is just once a week. And so look at what happens in this location. The logger just shows that the water level went above the ground surface. I mean, it's without question. Why? Because of the sampling frequency is different here, the water level does not go above the ground surface.
When you say water level, do you mean water table?
Yes.
Okay.
So that's a good distinction. So when I'm saying water level, I'm always referring to the water table. That's the groundwater level.
The water, and those graphs show the water table relative to the surface.
That's right.
Which has been normalized to be flat.
Yes, exactly.
With the surface, the spot of that particular.
Right, it is.
At that particular location. Yes. And so again, we have these precipitation events, and so when you get a precipitation event, you get these blips, so it goes up, precipitation event, large precipitation event, another large precipitation event goes up, and so they sort of coincide, and in this particular case, it goes above the land surface. Whereas in other cases, depending on that relative distance, it might not get even close to the land surface. And so we can discuss some of the implications of what's going on there afterwards when you look at the individual maps. I didn't want to spend a lot of time putting all the 20 plots that we have on the slide, so I have them on the tables for that discussion. And so I'm going to change gears and go to the citizen science literacy. And so how did this activity and exercise influence people's perceptions? So what we did was we gave the citizen scientists a pre-test, so we can get a baseline, and then afterwards we're going to give them the same test and see whether there was any change. So owing to the fact that we didn't have sufficient responses for the post-test, I can't say much quantitatively. We had another mechanism to assess the perceptions, but then quantitatively, we couldn't say this is how much they had improved. Let's say in the first instance they got 50%. Our hope would be in the next instance they'll get maybe 80%, and then say, oh, there's a 30% change. We can't do that because we didn't get enough responses. Next slide. So in order to address that, we had a focus group. So there were less number of participants in the focus group compared to the number of people that volunteered. But we think that the results are still valid because in a focus group, you are able to engage the person rather than ask them one question where they can fill out this questionnaire in 5 minutes. With a focus group, it's a longer period of time. You can engage back and forth. You can get different sides of the view and so on. So we had some really good discussions. And this focus group was facilitated by one of my other students, who's a PhD student at ECU. And it was held at the North Carolina Coastal Federation, and it was about a 2-hour session. And so what I'm going to show next are some of the comments that people made. And so they are not attributed to any person in particular. I just sort of put them in a big blob. And so if there are any citizens here, you might see your comment, but it's not attributed to anybody. I don't know who said it. Okay, so next slide. So these are some of the things that I thought were interesting with respect to what people said. The ones that are in red. Initially, people said that they had never thought about percolation to begin with. So it rains, and then that rainwater goes into the ground surface, and then it recharges the water table, and then the water table moves up. So precipitation is the major driver of the elevation of the groundwater level. and that's because there's percolation into the groundwater. Part of the study has to do with determining what the normal water level is. So how do you know that normal water level? We have to collect water level over a long period of time, and hence the engagement of citizens. There's two types of flooding. You can have just the regular flooding or the groundwater moving up. So that was one thing that they pointed out. Next slide. And so some folks said, well, there's lots of flooding due to groundwater, which that's what the town says. And so if we corroborate that assertion, then it must be true. And so that was a comment from one of the participants. Talked about the quality of groundwater. Next slide. And they also made comments about, in terms of problems and barriers and challenges, the measurements that they were taking. So you have to measure depth too, and then when we come back, we give you an elevation of the water level. So it wasn't consistent, it was somewhat confusing. And so we had to, next time we do this, we'll have that discussion so that people know that even if they're getting a depth too, it's easy to conceptualize an elevation so that everybody's on the same page. And the other thing that was a little confusing was that the meters that we have that you dip down, when you look at the readings, they're in decimal feet. So it's going to be 3.5 feet, not 3 feet and 6 inches. They don't have them. They don't have the meters that have 3 feet, 6 inches. So I took it for granted that people would figure that out, but it was, when I was looking at the data, the numbers were not making sense. And so again, it's just communication and facilitating the engagement. So that was very useful feedback. And again, I'm a scientist, so the output is in meters, but then you're recording the data in feet and inches, and so when you're looking at these plots, if they're in meters, when you're recording in inches and feet, it's really confusing. So we have to be consistent. So again, useful feedback. So here's the meter, just showing that when it's going to be decimal feet. So this is 1.5. So there are 10 dots here. They're not 12, right? So it's 1.5, 1.4. Okay. Slide. And that's why I spent a lot of time discussing the elevation 2 and depth 2, because based on the feedback, that wasn't really discussed, right? So why are we measuring depth 2, but then you're giving us elevations and so on and so forth? So it's a big issue that we should have addressed, and so moving forward, that's something we'll focus on. So again, great feedback that we're getting back. So this is a sketch that sort of illustrates how we get over that hump. So here's your well, and then here's the water level that is in the well. So the water table extends across in this direction into and out of this plane as well. It's a table, so it's a surface. But then the well just records the height of this water up to there. And so if you have a meter, you're going to be at the top, and then you're going to measure depth too. If you have a logger, it's going to give you an elevation of the height. And so everything has to be referenced to some data. And so we'd say, what's the height from sea level? If sea level is here, what's that height to that level? So there's some math that we do in the background to fix that. Next slide. So again, some other useful feedback. You can talk to me about it. I won't dwell on this. I think most of the comments that were made were pretty useful. So I'll just skip over this. Next slide, please.
Oh, on that first one is probably the biggest question now.
All right, so let's look at it then. Does groundwater table contribute to stormwater flooding on both banks? There are mixed opinions. And so it could be that there are mixed opinions because we have these points in space, and depending on where you are, if you're on a dune, obviously you're not going to have groundwater flooding on a dune, right? And then if you're close to a swell, you might have more. The issue again is that when we're selecting those points, we're not going to the locations where we're not really going to the swells. For access, right, we would say, well, why can we get our truck in, so that if in a swell, it might get stuck. So we're not going to go to the swell. So if we put a well in the swell, we'll definitely be having these water levels rising. But then it has to do with our sampling and where we decided to put our well locations. And so
Can your data tell at this point, if you do a point charge to the water table, by filling up a lake or by having shallow area, how long does it take to get a distance away from that charge to raise the water table over here? I know you may not know the exact number, but is it minutes or hours or days or weeks? And I know it depends upon what the ground is.
So are you trying to determine how much
long it
precipitation
takes
it
for
would
that
take?
point recharge of the water table at a point to get to someplace else? It doesn't happen instantly.
Now, so I'm trying to figure out a natural scenario where that might occur, because the driver is going to be precipitation, so precipitation is going to fall over an area, not necessarily on a point. So even if it's a smaller area, it's still going to
In a
be
very shallow area, to reference to the water table, it rains heavily,
right,
so it's going to charge at that point
Right.
before it charges other points.
right.
Another thing is we pump water into lakes, like on the golf course and so forth. That's a point charge too. I just have no idea how long it would take to get to the other side of Pine Knoll Shores. I don't know if it's weeks or minutes.
So the way that we can address that, this is another question that James is going to address, and he's going to build a groundwater model. So the usefulness of this data are that they'll help us constrain this model, so that we're not just picking numbers from thin air. So we do have the sediment material, and from that we can say this is the property of this sediment, put it in the model. We do have the water level data. We're going to take that data and calibrate our model so that the model is giving us appropriate numbers. And then once he creates that model, that will be an easy question to answer.
Yeah, I understand. Thank you.
Just closer to home here, one issue we face a lot of times is where somebody has bought a lot that's relatively low, close to the water table, and they bring in fill dirt before they, and raise the surface level in order to have a buildable property. Does that have any impact on the water table per se? Does the water table stay where it was and
Sure, that says yes.
you just have fill on top of it? Right?
So the water table will rise to the level that it was going to rise to even if you didn't have the sediment there.
Yeah.
And so in this case, it's just going to be under the ground, whereas before the sediment had come in, it would have been above the ground. So in terms of the level, the level doesn't change.
It affects water runoff, but it
Right.
doesn't affect the water table.
The height of the water table, that's right.
I have a question maybe for James. As luck would have it, you picked about the wettest fall here, I think, in the past 20 years, based on the readings they're taking it out at the airport at this time, so you were lucky in that regard. But this first bullet really surprises me, because I thought it would be a resounding, absolutely it does. The groundwater table does affect stormwater flooding. So that's kind of surprising.
Well, these are the perceptions
The perceptions,
of,
okay.
of those citizen scientists, right?
What I wanted to ask was, thinking years from now when loggers can be automated and we don't have to have people go to the field or whatever, and readings out in areas of town can be shot to a computer somewhere here at Town Hall, is there any value as a predictive measure for flooding to monitor water table, in your opinion?
Well, I think that goes back to the model that I'm going to be building ultimately for the thesis that I'm involved with. That model should help us answer that question.
Okay. But then the short-term answer is yes. So there is value, just as you've suggested. So this is a peculiar year, right? So we have our baseline, but then the baseline is for the peculiar year, right? So that's why you need to have a much longer time period in order to sort of address those really highs and really lows, so that you have an appropriate baseline over a long period of time. And so right now we can say that the data that we have is an appropriate baseline. It's a starting point, but hopefully we'll have a much longer time series to then get something that's normal. And so then the answer to your question is yes, it would be worthwhile having these water level readings and measurements taken.
So what would be an appropriate length of time to get that baseline that you're looking for? Do you need more months, a year, multiple years?
Ideally, you want multiple years.
Okay.
Because again, so we have 1 year, it's been really wet,
Yeah.
right? And so it can be months, because if it's months, then you're just looking at one season. What about the other seasons? So if it rains in the fall a lot, and then you do the summer, right, then you're missing those variations. And so ideally you want perhaps at least 3 years, because then if it's really high this year and then really low next year, that's still not normal. So you need perhaps 3 years then, so everything can average out. But if you can continue collecting data, by all means, collect all those
Well, you
data.
just need the thing.
I'm going to talk to Sarah about that. Yes.
The wells themselves, is there any difference between the wells that you installed versus somebody who has like a landscaping well to water the grass and stuff like that?
That's a very important question. Yes, there's a difference. And so when you install a well, you have to know the extent to which that pipe is slotted and to what depth it goes. And so if it's, as a scientist, we have to be really careful where we stick our wells in, because you've got these packages that are different aquifers. And so we have to be in the one that we're really interested in. And so sometimes those differences are subtle, such that, James and I will be like, well, we're in a different aquifer right now, let's put our well up to this level. If it's somebody else putting the well and they will give us that information, we don't really know where they were sticking that well in. They could be very deep, or they could be really shallow. And so again, it has to be apples and apples. So if we don't know, then, but if they have the records, perhaps you can look at the records, and perhaps you can get some of the sediment if it's a shallow well, and then say, well, from these records and the sediment that we took using a hand auger, we can infer that they're in the same unit, and then we can include it in the database.
Plus those wells, you probably know this, so those wells are much more expensive, have pumps and all that. These are simply, correct me if I'm wrong, passive monitoring wells.
Right. That's right.
We have had those wells, some of those wells in town go dry during the dry years, I've been told. I haven't seen any of those since I've been here, but I've heard of some irrigation wells that were only down 20 feet or so, probably maybe on high elevations. So they're pretty different. They're significantly different. These are PVC pipes 8 feet into the deck, or 20 feet, pretty much.
I actually have a quick question for you too that involves the pipe depths and the perforation. If one of the next steps for us is looking at groundwater quality, and we're interested in taking samples and potentially using the pipes that you put in, and ideally, hopefully getting some sort of gauge for the filtration of microbes, I guess, as it moves through the soil, will the perforations mean that we get a shallower, I guess, depth for that data than we would if it were a solid tube, or pretty much whatever depth we take a sample from in the column?
So it's going to be, the sample that you take will be representative of the column that's exposed to the well. And so, depending on what question you want to answer, in some instances, what we try and do is we try and make those perforations a much narrower length. And so we can say from this depth precisely, that's where that sample is coming from. Whereas right now, it's open from the water table to, let's say, 20 feet below that. So where exactly is that contaminant, let's say there's a contaminant coming from. So it could come from whatever depth, and then it comes in the pipe, then it mixes. And so you don't have an exact location where that came from. The alternative would be to have the well screened at a certain location, then the next one is screened right here, then the next one is there, and the next one is there. So you can actually tell that you picked up this contaminant at that specific depth. And so it might depend on what type of question. If you just want to detect it in the groundwater, then this will suffice, because let's say you've got high nutrients. So that's all you need to know. You've got high nutrients, that's fine.
But if you wanted to find a particular point of contamination, we would need to make some modifications.
Right, exactly. So some challenges with respect, as I start to wind down, a couple more slides. Some of the challenges were that some of the research involved human subjects, so the participants were giving their opinions, and so in order to get those opinions, we have to go through lots of bureaucracy and paperwork, and then as well we have to then have them participate, and so if they're not participating, then the quality of our data sort of degrades, and so we have problems with retention and attrition of volunteers. Some of the other issues involve data. As I said, it was with the feet and decimal feet, and so it wasn't a big problem to fix. But then it was a concern because people were entering things that shouldn't have been entered. But in this case, it was a big problem. In other cases, it might have killed the entire project because again, you need to have precise measurements. But we figured it out and then we addressed it. And so moving forward, that's something that's on us in the communication to the participants. Some of the things that we could not address, sometimes data were not always collected. Perhaps people left town, or perhaps they had other things, which is fine because again, it's voluntary. But then that's the trade-off. If we're going to have these water level loggers, you're paying $500 for a logger, but high quality. And then, but if you have volunteers, we're engaging more people, but then it's voluntary. And so if they don't want to, they don't want to. There's nothing wrong with that. And so it's this trade-off that we have to work with these citizen science projects moving into the future. All right, so what did we learn from those issues? We have to communicate effectively and also use multiple modes of communication. So that was on us as developers of this project. We have to make things as simple as possible and also provide a mechanism for formal withdrawal. If somebody said, I'm not going to do it, at least let me know so that if I need to, I can go and find out if I can get somebody else to replace you, or I'm not expectant of the data because then I get anxious. I'm like, didn't you send me the data? And then I'll be pinging you with emails trying to get those data. But so we didn't have that mechanism, so that's on us. All right, we can skip over that. And so there were some questions that were asked with respect to direction of groundwater flow. And so when I ran this data really quickly, we're still processing the data with respect to the maps showing the water table. So this map shows the topography in Emerald. So where it's really light, that's you're on a dune, and when it's dark, it's a swell. So you're going up and down, up and down. And then so here's the water table. So at this location, you got these concentric circles, it's 3 meters, and then as you're going further away, it's 1 meter. So this has, it's at 3 meter elevation, 1 meter elevation. That's 9 feet, 3 feet. Okay, and so we can determine the groundwater flow directions from these lines. Groundwater flow is going to be perpendicular to that line, and so in this case, it's sort of this high mound, and groundwater is flowing in all directions away from that high mound. And so this was in Emerald. So what we're trying to do is now extend this map all the way across to see if we're seeing these types of features. If we were to cut this island across this line and look at it from the side, this is what we'd see. So this line shows the ground surface, and then this blue line shows the water table at a specific point in time. And so again, here's the water table, it's below the land surface, and then here it's above the land surface, so you might get flooding in that location, and then here it's below. So we can have these maps that sort of show at certain points in time where the water table is above the land surface or below the land surface, and there'll be hotspots.